So now that we have an introduction to the idea of systems of equations, we're going to look at a new way of solving it. Now, this is something that you probably haven't seen before. The algebraic way of solving them with graphing, substitution, and elimination, that's stuff that would be covered in a basic algebra class. Matrices, this should be a fairly new concept for you for this class. So we're going to have to take our time getting through it. The nice thing about using matrices to solve systems of equations as opposed to the other ways that we've done is as the system of equations gets bigger, more variables, more equations, those other methods, while they become harder, the matrix method becomes very, very much the same over and over and over again. It's also very procedural in that you do the same things over and over and over again, regardless of how many variables and equations you have. So again, in the last section, we pretty much focused on 2 by 2, which is 2 equations and 2 variables. We're going to start to talk about 3 by 3 and so on. Okay? And the matrices will allow us to do that. So what is a matrix? A matrix is a rectangular array of real numbers arranged in a certain number of rows and columns. So let's say m rows and n columns. Okay? We say the dimension or size of the matrix is then m by n. M, the first letter, represents the number of rows. The second letter represents the number of columns. Here would be our rows, and then here would be our columns. We can then look at each member of the matrix and identify it by which row and column it is in. So if you look at, say, A12, that means A12 is in row 1, column 2. Or A23 is in row 2, column 3. So AMN is in row M, column N. We typically will use a capital letter to denote the name of a matrix and lowercase letters to denote the elements of a matrix. And then we put brackets around those elements in their rows and column form to say that this here is our matrix. Okay, so the first thing we want to do is we want to look at converting our system to matrix form. Now, in doing that, we're going to call this writing the augmented matrix. So, again, a matrix serves as a device for representing and solving a system of equations. And what we're going to do is we're basically going to remove the variable component, write as little as possible as it relates to the variable component, in order to solve the system. If we know that the first component is the x term and the second component is the y term, there's really no reason to write then the variables x and y. So we'll express the system in matrix form. We extract the coefficients of the variables and constants, and we'll use those as entries in the matrix. We'll use a vertical line to separate the coefficient entries, so the left-hand side, from the constants on the right-hand side, essentially replacing the equal sign with a vertical line. When the system is written in this form, we'll call that the augmented matrix. If this seems confusing to you, it will not be within a few minutes. So, we're going to write the coefficient in x terms as numbers down the first column, write the coefficient of the y terms as numbers down the second column. If there happens to be z terms, then maybe that'll be the third column. So we may have more variables. This will just continue to grow. We draw a vertical line and write the constants from the right-hand side on the right side of that line. So very simply, if we looked at a 2 by 2 system of equations, which means we have 2 equations and 2 variables. Let's say it was this system right here. First thing, we set it up so that our x's are lined up, our y's are lined up, our equal signs are lined up, and then the constants on the other side. If this is the case, if you look at just the left-hand side here, we could rewrite that by stacking our x's over into the first column as far as the coefficients, so 3 and 4, and then we could stack our y coefficients, 4 and -2, in the next column, creating what we call the coefficient matrix. However, we're going to expand this into what we call the augmented matrix by then simply drawing a straight line after that coefficient matrix and then writing the constants on the other side, 7 and 5. So this right here would be your final augmented matrix. This is the same thing as if we write this system here, but we'll extract the x's and y's and just know this first column represents the x's, the second column represents the y's, the straight line is the equal sign, and then the other side is our constants. So you can see it's a very easy thing to do to switch a system of two linear equations with two variables into an augmented matrix. Here we will do it with a 3 by 3. In this case, we have 3 variables and 3 equations. There are variables x, y, and z. Now, notice, there is no z in this first equation, and second equation, and there is no y in this third equation. But let's look at the first equation and see that we have 3x, -1y, -1z. So we could write that as 3, -1, -1 as our x, y, z coefficients. In the second equation, we have a 1 for the x, a 1 for the y, but since there is no z, there is a 0 there. So we have 1, 1, 0. And finally, we have 2 for the x, there is no y, so 0 for the y, and then -3 for the z, and that would be our coefficient matrix. Expanding that then into the augmented matrix, we keep this as our coefficient matrix. Again, 3, -1, -1 for the first equation, 1, 1, 0 for the second equation, and 2, 0, -3 for the third equation. Straight line, and then the constant 0, 5, and then 2. And there is your augmented matrix for this system. Again, should be very easy to do. The more variables I give you, the more equations I give you, you should still be able to do this. Again, understanding that this first column represents your x, the second column represents your y, third column represents your z. We could just continue to expand this with more equations and more variables. The next thing we want to do is start to talk about performing what we call row operations on a particular matrix. So now that we know how to write an augmented matrix, we'll examine various row operations that we can perform on a matrix using addition, multiplication, or interchanging rows. These are all operations that can be performed without changing the solution to the system, but make it easier for us to find a solution to the system. So performing row operations on a matrix is a method we use for solving a system of equations. Since these operations allow us to change a complex system into an equivalent simpler system, it's a very good way of solving a system. In order to solve a system of equations, we want to convert the matrix into what we call row echelon form. We'll discuss exactly what that is, in which there are ones down the diagonal of the matrix, so the main diagonal, and from upper left to lower right, it's always that direction is your diagonal. There will be zeros below it, and then random values that result above it. So that is called row echelon form. Again, ones in the diagonal, zeros below, some random values above based off of whatever operations we performed. So how do we get to this point? Again, we're going to get to this point through a series of addition, multiplication, and interchanging rows. So here are some basic guidelines for row echelon form. 1. In any non-zero row, the first non-zero number is a 1. It's called the leading one. Okay? In all zero rows need to be placed at the bottom of the matrix, and you could just move one row from one place to another, and we'll talk about that. Okay? Any leading one is below and to the right of the previous leading one. Any column containing a leading one has zeros in all other positions in that column. Okay, these will all be things that we're looking to do or find. We will talk about getting through each one of those things as we go. Again, if it's not clear to you right now, it will be clear as we move forward. So in solving this, what we like to do is to write down exactly what kind of operation we applied to a given matrix. If you're going to interchange two rows, we tend to write this notation right here to say that that's what we did. We interchanged row I with row J. We put the double arrow showing that we swapped those two rows. If you multiply a row by a constant, then we write the notation as whatever constant it was times whatever row we were working with, row I, so row 1, 2, 3, whatever, and we write it in that notation. If we're going to add one row to another, okay, in this case, let's say we add one row with a constant multiple of another row, we could say Ri plus C times Rj. In that we took row I and we added it to this constant times row J, okay? And that would be the notation we use there. It's very important that you get used to writing down what operation you used as you change your matrix, okay? Eventually trying to get it into that row echelon form. The process of getting it to row echelon form is formally called Gaussian elimination. It's the strategy that we're going to use to get to that row echelon form. Again, the goal of getting some random matrix here that has a certain number of rows and columns into a diagonal of ones with zeros below and constants above. Notice that the diagonal is referring to basically a matrix that is square. And we'll talk about that in terms of a square matrix where we have the same number of rows and columns. If we don't have the same number of rows and columns, the diagonal will still start from the beginning term, make that beginning term here a 1, and form a diagonal from there as far as you can, with again zeros below and ones above. Okay? I think the best way to explain all of this is with a specific example. So we're going to go through a series of steps, in which case using our row operations on the augmented matrix to achieve our row echelon form. We're going to try and get a leading coefficient of a 1 in the first equation. We're going to interchange rows or multiply by constants to get that. We'll use row operations to achieve zeros down the first column below the 1, and then we'll try and get a 1 in the second column, second row, and then continue with zeros below that. Then we're going to get a 1 in the third row, third column, and zeros from everywhere else. So basically creating our row echelon form by getting 1s in the diagonals and zeros below. So let's see how this could be done. I'll start with a very simple example, a 2 by 2 example, which we already know how to solve using substitution or elimination by addition, but let's see how it would be solved using matrices. And what you're going to see is basically what we're doing is very similar to a combination of the elimination by addition and substitution methods. So let's look at a system. Here is our system. Okay. Let's first write the augmented matrix. And you see we have 2x plus 3y equals 6, and 1x minus 1y equals a half. All right, so there is our first step. Write the augmented matrix. I want to interchange my two rows, row 1 and row 2. Now, why did I want to do that? I flip-flopped row 1 and row 2 because I already had a 1 in the first register in row 2. So by moving that up to row 1, the first part of my diagonal of 1s is already taken care of by simply just flipping the two rows. And I say that's what I did by this particular operation. I reversed row 1 and row 2 in their position and gave me this matrix. That's all I did. All right, now that I have a 1 in that first position, I want to get a 0 below it. Well, the way I can get a 0 below it is if I multiply row 1 by -2 and add it to row 2 to get my new row 2. So if I take this value here and I multiply it by -2 and I add it to this value here, -2 plus 2 would make 0. Now if I do that, I have to do that for everything. I'll take this, multiply this by -2, and then I'll add it to this value here, giving me 5. I'll take this, multiply this by -2, which would give me -1, then add it to this value, giving me 5. So the entire row 2 has now been changed by simply using this particular operation. Again, -2 times row 1 plus row 2 gave me my new row 2. And I did that for every single value. So now this is the new matrix I'm working with. The next thing I want to do is I want to get a 1 in this register so that I'll have 1s in the diagonal and 0s below. Well, the way I can turn this value into a 1 is simply by dividing it by 5. So if I take row 2 and divide it by 5, which is the same thing as saying multiply by a fifth, I'll get my new row 2. And so if I divide this by 5, I get 1 here. And if I divide this by 5, that'll make this 1 as well, thus giving me now this new augmented matrix. Notice this new augmented matrix is now in row echelon form. But simply look at what the last row represents. That last row here represents that this is my x column, this is my y column, this is my equals, and this is my constant. Well, simply looking at that, that's basically saying 1y equals 1, thus giving me the solution for that variable. If I then back substitute that in to the first equation, okay, which is saying right now, you probably can't see it, so let's erase some things. What that first equation is now saying is that x minus y equals a half. Well, if I take this and I substitute it in, well, x minus 1 equals a half. Tells me that x equals 3 halves. Well, now there's my solution. X is 3 halves, y is 1. Let's look at another one. Here we have nothing in terms of a 1 in the first position, but it's still a 2 by 2 equation set up. So again, one of the easier forms. We will not expand this out yet, but let's look at this. So first, we have our system. 2x plus y equals 1. Let me switch to highlighter. Erase this. 2x plus y equals 1. 4x plus 2y equals 6. We could easily switch that into this augmented matrix here and here. So I want to first make this first value a 1. So in order to make that a 1, that would be my first step, I want to divide that by 2. So I'll take row 1 and divide it by 2, and that'll give me my new row 1. That means everything in row 1 has to be divided by 2. So 2 divided by 2, that would give me 1. 1 divided by 2 would give me a half. 1 divided by 2 would give me a half. Okay, here's my new matrix. Next thing I want to do is I want to make this value here a 0. So if this has to be a 0, what I'm going to do is I'm going to take this value here, multiply it by -4, then add it to this value. So -4 times row 1 plus row 2 will give me my new row 2. And that'll give me -4 times 1 plus 4 gives me 0. But I have to do that every single time. So I'll take this. I'm going to multiply this 1/2 by -4, which is going to give me -2. And then I'm going to add it to this value here. Well, that's going to give me a 0. Then I'm going to do it again. Take this value, multiply it by -4. Again, giving me -2. Then I'm going to add it to this value, giving me 4. So now this is the new matrix I'm working with. However, if you look at the second row, because everything is a 0 now, I don't have 1s on my diagonals. What I basically get is 0x plus 0y equals 4, or simply 0 equals 4, which clearly is not true. Here's the first example we have seen that we have an inconsistent system. Basically, there's no solution to this system. However, what if when we did these operations, when we took -4 times row 1 plus row 2 and got our new row 2, instead of getting a 0 here, here, and also here, okay, what if we did get a 0 in this register as well? In which case we would have had 0x plus 0y equals 0, or simply 0 equals 0. What would that mean? Well, that would tell me that the two lines are the same line. And then therefore we have a consistent system. All right? And we have infinitely many solutions. So there's a couple of things that can happen here in this row echelon form where we could end up with one solution, no solutions, or infinitely many solutions depending on how this whole matrix zeroes out. Something like this, no solution. Something like 0 equals 0, infinitely many solutions. Or we could end up like the previous example and just figure out what, say, y equals.
We have a 3 by 3 system in that we have 3 equations with 3 variables. The setup is basically the same in terms of what we're going to try and accomplish. First thing we're going to do is we're going to create the augmented matrix. So the first equation is 1x minus 1y plus 1z equals 8. So 1 minus 1, positive 1, 8. Then 2x plus 3y minus 1z, so 2, 3, negative 1, equals negative 2. And then finally 3x, so 3, minus 2y, so minus 2, minus 9z, minus 9, and 9 on the other side. So there's your augmented matrix. First column represents x, second column represents y, third column represents z. So our first goal is to get a 1 in this first register. It's already there. Our next goal is to make this a 0 and this a 0 underneath. So we need to change row 2. The way we change row 2 is to multiply row 1 by negative 2 and add it to row 2. If you can't see that, let's change it to a different color. So negative 2 times row 1 plus row 2, that'll give me my new row 2. So if I take negative 2 times this and add it to this, I'll get 0 here. But then I'll take negative 2 times this and add it to this. Well, negative 2 times negative 1 gives me 2. 2 plus 3 gives me 5. Then I'm going to take negative 2 times this and add it to this term. So negative 2 times 1 gives me negative 2 plus negative 1 gives me negative 3. So that's where this came from. And finally, negative 2 times 8 plus negative 2 gives me negative 18. Okay, so there's my new row 2. But I also want to change row 3. I want this to be a 0 here. So if I take negative 3 times row 1 and add it to row 3, that'll give me my new row 3 to be a 0. But I have to do that again to every term. So if I take negative 3 times each one of these values here and add it to this, strike that. Things are getting a little messy here. Let's clean this up. If I take negative 3 times each one of these values, row 1, and add it to row 3, that'll give me my new row 3. So that'll give me 0 on the first register. Then negative 3 times negative 1 is positive 3. Positive 3 times negative 2 gives me positive 1. Negative 3 times 1 gives me negative 3. Negative 3 and negative 9 gives me negative 12. And then negative 3 times 8 gives me negative 24. Negative 24 and positive 9 will give me a negative 15. So now I have a 1 followed by 2 zeros below it. Next thing I want to do is I want to get this term right here to be a 1. Well, I can simply get that term to be a 1 by dividing by 5. However, if you notice, the row 3 we had before had a 1 in that middle position. So if I just interchange row 2 and 3, so row 2 interchanged with row 3, then I can actually get a 1 there without having to do any real operation. So that's easier. If you didn't see that, then we could have divided by 5. But if you noticed that, then you could have simply just swapped those two rows. To me, that's the easier way to do it. Right. So now what I want to do is I want to get to be a 0 here. So how do I get to be a 0 there? Well, if I take this times negative 5 and add it to the 5, that'll make a 0. So negative 5 times row 2 plus row 3 gives me my new row 3. But then I have to do it to each one of these. So negative 5 times this plus this gives me this term. Then negative 5 times this plus this gives me this new term. So that makes those both 57. All right, almost there. Last thing we need to do is make this term now a 1. So if we make that a 1, we can simply divide by 57. So 1 over 57 times row 3 gives me a new row 3, essentially making this a 1. But then this has to be divided by 57, which also makes it a 1. Now, if you look at this matrix that we have, where we have 1s in the diagonal and 0s below, and rewrote it with x, y's, and z's, the first equation would be x minus y plus z equals 8. The second equation would be y minus 12z equals negative 15, and then z equals 1. Well, right there, z equals 1. That's one of your variables solved for. Take that and plug it into this equation here. Well, y minus 12 times 1 equals negative 15. Solve that for y, and you're going to get negative 3. Then take that and plug it into the next one. Well, that's going to give you x minus y, so plus 3, plus z, which we already found to be 1, equals 8. And now you solve for x and get 4. So now you have your solution, 4 minus 3, 1 as your x, your y, and your z, and that's the point that all three of these equations share. Once you get it into this row echelon form, it's very easy to see the solution by getting this variable, plugging in here, then getting that variable, plugging it into the next one, and you solve your system. You can go back to the original system of equations and take this point and plug it into each one to double check your work. Let's look at an application of three variables, three equations. So Peter is planning on investing in what's called a three-fund portfolio, consisting of a U.S. stock mutual fund, an international stock mutual fund, and a bond mutual fund. He has a total of $200,000 to invest and wants 4 times as much invested in stocks as in bonds. The bond fund has a historical return of 4.4%. The U.S. stock fund has a historical return of 8.3%, and the international stock fund has a historical return of 5.4%. If Peter is hoping for a $13,300 return, how should he allocate his investment? Okay, there's a lot happening in this question, so let's break it down piece by piece. First, historical returns are not prediction of future earnings, but the best we can do in terms of trying to predict future earnings. So, we have a system of 3 equations and 3 variables. First off, the first variable, x. That can be the amount we invest in the U.S. stocks at an 8.3% return. Y, the amount we invest in international stocks at the 5.4% return. And then Z, the amount invested in the bond fund at 4.4% return. So we have a total of $200,000 to invest. So X plus Y plus Z has to equal $200,000. Now, he wants 4 times as much invested in stocks as in bonds. So if you take X plus Y has to equal 4Z, or you could say X plus Y minus 4Z equals 0. So let's keep moving. If we start working with the return rates, we know the 8.3% return rate, the 5.4% return rate, and the 4.4 return rate for each of those items. So you have to turn your percents into decimals, so the 8.3% to a decimal would be 0.083, etc. So then we get this equation. All right. So if we take those 3 separate equations we just created, so the 2 in the previous slide, and then this third one, the x plus y plus z equals 200,000, the x plus y minus 4z equals 0, and now this one, 0.083, 0.054, 0.044 equals z equals 13,300, we now have our 3 equations created in our augmented matrix. Now, obviously these numbers we're working with are not the easiest numbers to work with. That's one problem when it comes to these word problems, is lots of fractions, lots of decimals. But just see if you can follow along with me. First off, we want a 1 in this first register. We already have it. We then want to get a 0 here and a 0 here. Okay? So if we try and get a 0 here and here, what are we going to do? Well, what we're going to do is we're going to take a negative 1 times row 1 and then add it to row 2. So negative row 1 plus row 2 equals our new row 2. I'm going to do that term by term by term. So that would make this a 0. This one here will give me a 0. This one here will give me a negative 5. And then this one here will give me negative 200,000. Then I want to get a 0 in this position. So if I take negative 0.083 times row 1 and add it to row 3, here to here, I'll have to erase this so you can see it better. So we're going to take negative 0.083 times row 1, that's row 1, and then add it to row 3 and do that over and over and over again. We would then get, and this is where it's going to get hard, we're going to get 0 here. If you had a calculator, you could see what negative 0.083 times 1 plus 0.054 is, and that would give me negative 0.029. Same thing here. This times negative 0.083 times 0.044, you would get negative 0.039, and finally the last one would give me negative 3,300. I don't expect you to do this in your head right away. You could do this in a calculator, though, very easily. All right. Next thing we want to do is we want a 1 in the next position. Because this is a 0, that's not going to be able to be turned into a 1. So what we're going to do here is we're going to flip-flop these two rows. So we're going to interchange row 2 and row 3. So we already have a 0 here. All we have to do is make this a 1. We can make it a 1 by dividing by that value all the way across. We divide by negative 0.029, and we get our new row 2. So we divide everything by that negative 0.029. We get a 1. We'll get 39 over 29, and then we get 3,300,000 over 29. Okay? Again, just plug it in your calculator. You get those values easily. Finally, last thing we want to do is turn this into a 1. That way we get 1s in the diagonal, and we have 0s below already. So we just divide by negative 5, take row 3, divide it by negative 5, we'll get our new row 3. So here, divide by negative 5, we get a 1. Divide this by negative 5, we get 40,000. So if you look at this third row tells me that z equals 40,000. We already got one value. Then we take that and work with the second row. The second row says y plus 39 over 29, z equals 3,300,000 over 29. We'll take that z, plug it in there, and solve for, sorry, this is a y. This is y. Y, take that z, plug it in there, solve for y, and you'll see that you get a y. This is the work here. We'll see we get a y of 60,000. Now that we have a y, let's look at the first row, which is x plus y plus z equals 200,000. Well, we know the z is 40,000. We know the y is 60,000. Make sure we get enough zeros there. How many zeros? Oops, too many zeros. And then we got to solve for the x. Solving for the x, you see x would then be 100,000. So the answer would be 100,000 in x, which is U.S. stocks, 60,000 in y, which is international stocks, and 40,000 in z, which is bonds. Again, this was a lot more difficult than the previous examples, largely because of the numbers we were working with, but if you notice, the process was exactly the same process we were using with the previous examples. We could step this whole thing up into 4x4, 5x5. We're not going to go that far. You could take classes, specifically as a class called linear algebra, where you really get into solving these systems repeatedly. We are learning this as one lesson this semester, but you could spend a whole semester working with solving systems of equations using matrices and really getting into advanced row echelon form. As with our 2x2 systems, 3x3 systems have quite a few number of possibilities. Now, graphically, a 3-variable linear equation represents not a line, but a plane in 3-dimensional space. So if you're working with 3 separate 3-variable linear equations, you're working with 3 separate planes. And so if you look at it, one possibility is if you take all 3 of those planes and have them intersect each other, that they all could intersect each other at a single point, which is what we found for our linear systems. Okay? That is a possibility, is all 3 planes intersect at a single point. There's also a possibility that all 3 of those planes intersect as a line. Okay? That's the intersection of all 3 planes. Now, that would represent essentially an infinite amount of solutions because that line is made up of infinitely many points. So in this situation where the planes all intersect as a single point, you get one solution, and it's that ordered triple, and x, y, z. There's one x, y, z that solves the entire system. However, this setup, you have a line of intersection between the three planes, in which case you have an infinite amount of solutions. And in the Gaussian elimination row reduction form, you would get a 0 equals 0 statement as one of the rows in your augmented matrix. There's a bunch of other possibilities that all represent essentially no solution. Is if all three planes look like this, where they don't share anything. So this plane, this orange plane here, and this green plane here, they intersect here, but the green plane and the blue line intersect here, and then the blue and the orange plane intersect here, in which case there's nothing that all three of them share. So that would create a no solution scenario in the system. You could have something that looks like this, you could have something that looks like this. All three of these represent the same thing, no solution, in that they don't share, all three planes don't share anything. 2 out of the 3 do, but not all 3. And so what will happen is you'll get a statement somewhere in your reduced matrix that would be something like 0 equals 3. So if you're looking at your reduced matrix, you maybe get 1, 5, 7, 2, say 0, 1, 2, 5, and then 0, 0, 0, 3. In which case that would be 0 equals 3, telling you no solution. So again, really you can break it into 3 categories: one solution, infinite solutions, no solution. But there's numbers of ways that say the no solution can occur. And we're talking about planes, not lines anymore, so it does get a little more complex from a graphical perspective.